Hi everyone, this is Jake Fry, and today I'm going to discuss what functions are and what are types of functions that we use in physics. So first, describing motion. So in many cases, the points of position and velocity, or really any type of vector that you want to measure, will be discrete values that will be separated by either the resolution of the time, or how good your clock is, or just by the number of measurements that you're taking. And in fact, all experiments, data will be discrete points such as these. But in theoretical physics, it is much more common to describe a system, a physical system, using functional forms or functional fits to the data itself in order to make the expression look very nice and smooth for all the math. For example, if we had two variables, say y and x, and we were to plot them, this case on a log-log scale, but that doesn't really matter for right now, we can see that the data is scattered around, but it might look, reasonable to try to fit the data, in this case, to a line given by the equation y equals a plus b times x. And once we fit it to that line, we are now given a very powerful tool, this function, in order to do things like interpolate between data points or even extrapolate outside of where we took data. So, what exactly is a function? So a function, say f of x, is simply a rule that assigns to each element x in a given set D exactly one value f of x in a set R. And so the x values in this case are called the independent variables because the experimenter is actively changing this variable in order to see what happens to the system. The set D is the domain of the function, and so that's all the values of x that you can have. And this can be done by fixing what you want to look over in terms of your variable x, or it could be determined by the function that you have. And then f of x are the values known as the dependent variables of the function. Sometimes you'll also see f of x written as, say, y, but it can be confusing later if you always have y be a dependent variable. And the set R is the range of the function, so that's all the values that f of x can be given your domain. And so graphically it looks something like this for a given function y equals f of x, shown in blue. So the domain of the function is all the values in x in that red region, and the range is all the values of y in the domain itself. So that spans from the left endpoint of the blue line to the right endpoint, and then you see how high it goes in y. So one way to determine if something is a function, and in particular what I mean here is if it's a one-to-one function, and that means for a given variable input, you have only one output. So I think pretty much all functions that you'll deal with in the physical world will be one-to-one functions. So it's good to know how to determine if a function is in fact one-to-one. So the most basic way to do this is to plot the function in terms where the dependent variable is on the y-axis and the independent variable is on the x-axis. So in this Cartesian coordinate system or rectilinear Cartesian coordinate system, this way, if you have a vertical line and you pass it across the function, if the function intersects that vertical line at more than one location, then it is not a one-to-one function. So on the left, we have this vertical line at x equals some constant a, and we see that our blue function line only intersects at one point. However, if we have like the situation on the right, and we have a vertical line at x equals a, we see that the function intersects at 2 locations. And so that would mean that it is not a one-to-one function. So you can only, in fact, use the vertical line test if you force the system to have this rectilinear Cartesian coordinate system basis. So if, say, x isn't your independent variable, and instead, say, you have a bead and it's traveling along a curved path, well, even though the bead wraps around, say in our second plot, if the independent variable is just the position on the curve, then while it might appear that it would fail this vertical line test, in order to actually make the test valid, you have to, stretch out that line so that your horizontal axis is the position on the string and not just the x or horizontal position. So just be careful on some of the physical problems like this to make sure that you have well-defined what your dependent and independent variables are. Okay, so for an example, using a graph, we can have, say, the position versus time graph shown on the right, and we want to find out, some information from this graph. So if we wanted to know what f of 2 seconds is, all we would do is we would go to the horizontal axis, which has our independent variable time, find 2 seconds, and then make a vertical line upward and find where our blue line, which is our function, intersects with that vertical line. And so at 2 seconds, our function equals 2 meters. Similarly, for 5 seconds, we can do the same thing. And so at 5 seconds, then we go up, and our function equals 3 meters. Cool. All right, so now what are some commonly seen functions in physics? So physics is a very mathematical-based science, but don't be afraid by that. The whole purpose of it is just to make it easier to describe the physical world. All right, so now I will describe some of these functions. They include piecewise functions, absolute value functions, polynomials, rational functions, trigonometric functions, exponential functions, logarithmic functions, and finally conic sections. And there are far more than just these, but these are the most commonly seen ones in, classical mechanics. Okay, so for the first, piecewise functions, so this is whenever you have a jump in your function itself. So in this case, you have for anything x less than or equal to -1, the function takes a linear function, and then from -1 upward, but not including -1, it's a parabola. And so this type of function might occur if you're just trying to track a ball rolling down a ramp that then falls into, say, a bowl that's shaped like a parabola. So yeah, that can occur. So yeah, that would be piecewise functions. Then absolute value function. So this arises when you don't care if you know the direction of your independent variable x. You only care about the total magnitude away from the origin. And so that means if you go to negative value, -a, the absolute value will just get rid of that negative sign and make it positive. And if you go to positive a, there was no negative sign to begin with, so it's just a itself. And so that's why just the absolute value of x has this characteristic V-like shape. Next are polynomial functions. And a polynomial function is one that's given by this format, where a sub n is a constant for a given integer power n, and the value n is the degree of the function. So the maximum value of n is the total degree of the function. So say if n equals 0, then your function is just a constant, so it would just be a horizontal line. if n equals 1, you would have a degree of 1, and you would end up having something that was a line, but with a slope. And further, the next one, n equals 2, you'd have a parabola. N equals 3 would be, cubic, and so on. So these functions are very commonly seen. And so we can then expand upon those polynomial functions by creating new functions called algebraic functions, which are a giant class of functions, which basically are constructed by using algebraic operations on those polynomial functions. So you can multiply two functions together, you can take the square root of the functions. So remember, I guess the polynomials have integer values in the exponents. So if you have, fractional or decimal values, that would be in the exponent, that would be an algebraic function instead. Okay, and so I guess I'll describe some of the most common algebraic functions. So there's the reciprocal function, so like y equals 1 over x, and so this type of function will give you things like asymptotes, as shown here, in both the horizontal and vertical direction. And then further out, rational functions. So this, the reciprocal function is just a special version of the rational function, but it's, I guess, easier to look at to recall asymptotes. But a rational function is simply the ratio of two polynomial functions. So you'll usually have to figure out things like asymptotes or wholes by simplifying the functions and doing things like long division. All right, now next, a very important class of functions are the trigonometric functions. And so these were developed in order to describe points, of course, along a circle, but also can be used to describe geometrical shapes. You can use them to decompose vectors upon a coordinate system that you want, as well as more easily describe things that are having sinusoidal motion, so things like waves or a pendulum. So these are very important functions, and I guess here are the definitions of each. For a given angle, what are the the values given, when you put down a right triangle, what does it look like? All right, and then next are exponential functions, and these are functions of the form of constant value that's raised to a power which is given by the independent variable. And so this is very common in like population growth if it's exponential. So the most common bases are things like base 10, base e, which is Euler's number, base 2, and base 1/2. And then on the other side of the same type of function are logarithmic functions, which are the inverse function of the exponential function. So for example, if you have an exponential function b raised to the y equals x, that function would have an inverse, which would be y equals log base b of x. And so these ones are also very commonly seen in things that are similar to population growth, but with a limit. So instead of exponential, they're petering off at long times. All right, so now next are conic sections, and so that sounds fancy, but all that it means is it's a type of function that you can generate based on taking different slices of a cone. That's why it's called the conic section, because you're taking a section of a cone. So the most basic version of a conic section is just a circle. So you slice the top of the cone to get the circle, and so it's centered on the point h, k, and has a radius r, and it'd be given in this form. And then if you slice at an angle, you would have an ellipse, so you'd have two different, directions One is the long direction, here could be A, and the other is the short direction B. So not just a single value of the distance from the center of the ellipse to the circumference. And then a sharp cut would give you a parabola like this. And then finally, for a very sharp cut, you would have a rectangular hyperbola like this one. And so all of those functions are very common. You would see like conic sections, for example, in terms of classical mechanics, very often in astronomy. So yep. And so that's all for today. And yeah, thanks for watching.